video, we will discuss methods economists use to establish causal effects. Establishing a causal relationship between policy and an outcome is one of the most difficult tasks in social science. For at least 100 years, the gold standard approach to establishing causality is to use a randomized controlled trial, or an RCT. An RCT compares a treatment and a control group and randomizes people to one group or the other. Unfortunately, we can't always conduct an RCT due to practical or ethical considerations. In that case, we still have treatment and control groups, but rather than randomly assigning people to treatment and control groups, now people are free to select into the two groups. To help us understand the challenge, we're going to use a visual modeling framework called a directed acyclic graph. In these graphs, we can show a number of different relationships between two or more variables. In each figure, we will have boxes and arrows representing variables and arrows showing causal relationships. In these graphs, the arrows always have a single head and go from cause to effect. So what if X causes Y? Then we have a single arrow going from X to Y. Y causes X has the arrow going in the opposite direction. Finally, X and Y may share a common cause, Z, which also leads to a correlation between X and Y. Now, let's use these tools to help us understand experimental and observational studies. We're going to be concerned about the effect of a policy on an outcome. In both cases, we'll have unobservables, a Z variable that affects the outcome. What this means is that the value of the outcome depends on some unobservables that we cannot control for. This may or may not be a problem for an analysis of the effect of our policy on the outcome. The problem with the observational data comes up if the unobservables affect the policy too. Why is this a problem? What if a high value for the unobservable makes it more likely you're exposed to the policy and more likely you experience the outcome? Then we would overestimate the effect of the policy on the outcome because of these unobservables. Randomization solves this problem by randomly assigning people to policy so that the unobservables no longer affect the policy directly. Let's look at a real-world example. Does Medicaid reduce mortality? This is a hugely important question since the United States spends billions of dollars each year on the Medicaid program. But it isn't easy to answer because poverty affects both Medicaid and health outcomes. Let's first try the observational comparison. Medicaid beneficiaries are in general in worse health than non-Medicaid beneficiaries. This may be due to poverty, since people in Medicaid are more likely to be in poverty than people in non-Medicaid. So the issue is if poverty has an effect on health, then we cannot simply compare Medicaid and non-Medicaid health outcomes. We call this problem selection bias because people may choose to participate in a treatment or policy in a systematic way. Perhaps this is due to preferences. The effect of having a red car and speeding tickets, for example, may be because people who like to drive fast want to stand out, and they can more easily do that with a red car. Maybe it's a selection on the outcome problem. If I'm more likely to benefit from a policy, then I should also be more likely to enroll. Or it could be random noise, in which case we're back to our RCT ideal. Selection bias is the total effect of the systematic determinants of treatment. In our Medicaid example, it is the effect of poverty on health outcomes. Unfortunately, this means that we can't simply compare treatment and control groups. Because of this problem, we'll turn to experiments, the RCT that we talked about earlier, and quasi-experiments, where we have events that look like an experiment. We will look at two quasi-experiments. First, the effect of Medicaid expansion on Medicaid enrollment, and then the effect of age on Medicare coverage. How would a quasi-experiment work in practice? The key is that Medicaid expansion would affect Medicaid coverage, but not health outcomes. There's no arrow connecting Medicaid expansion to health. So we can use Medicaid expansion as a proxy for treatment. So let's look at some data on Medicaid expansion and mortality. First, always look at your data. In this figure, expansion and non-expansion states are in different trends before treatment, which took effect in 2000 and 2001 in this example. So what can we do about this? The big thing people do is they look at differences between the treatment and control groups over time. In this case, those differences are trending slightly upwards, but in general, flat. This leads us to difference and differences analysis. The idea behind difference and differences is to compare two groups, which we'll call treatment and control, over time. We can look at the graph from before and think about this comparison again. We have our treatment and control groups, and before and after periods. Let's take some differences and see if that helps. Let's subtract control from treatment, and then the post period from the pre-period. We can simplify this process by just looking at group means and taking differences between groups over time within group, and then the difference in these differences. This identifies a causal effect as long as we think the control difference from pre to post is a good proxy for what would have happened in the treatment group without treatment. So how do we do this in practice? As I alluded to, we only need 4 pieces of data: the control group pre-period mean, the treatment group pre-period mean, the control group post-period mean, and the treatment group post-period mean. And then we compute the differences in Excel or in a regression model. But sometimes we can't get a pre-period. So what do? We're going to think about this as the effect of Medicare on mortality. We could look at the pre-period, which is before 1966, but data from that area aren't that great. Instead, let's use the increase in Medicare eligibility at age 65. We see a large discontinuous increase in Medicaid eligibility at that age. This is very similar to the MLDA paper we read earlier that uses the discontinuous change in drinking at age 21. So we can think of the underlying problem as estimating the causal effect from Medicare to health outcomes, but we have these unobservables that affect both Medicare and health outcomes. In our quasi-experimental study design, we will look at how turning 65 affects Medicare coverage. Turning 65 has a direct effect on Medicare, but there's no arrow linking turning 65 to health outcomes. Therefore, we can think of turning 65 as a proxy treatment. Now, let's look at our mortality data. The dots here are actual data, and the lines are a fitted linear regression on the log mortality rate. And there's a small break in mortality trends at age 65. We're going to use a regression discontinuity to look at the effect of this policy. We will compare two groups, treated and control, using a running variable, which in this case is age. We can infer counterfactual outcomes, what would have happened without treatment at the discontinuity. Typically, we do this using linear regression in both the control and treatment groups, and estimate the fitted or expected value at the discontinuity in both models. The difference is in the causal effect of the discontinuity. In this case, 1,297.8 deaths per 100,000 per year with Medicare versus 1,381.2 deaths without Medicare, for a treatment effect of 83.4 fewer deaths per 100,000 people per year. This analysis relies on the idea that we can extrapolate from the control group to the treatment group, and this is where journal articles tend to spend most of their time in a regression discontinuity setup. So to summarize, difference and differences and regression discontinuity are two of the most common empirical tools in microeconomics. They're both relatively easy to do in either a statistical package or Excel, and you don't need to do any fancy programming to get the basics right. Good luck.